Good morning, everyone. This is David. I want to discuss the wind turbine work, which applies when setting the wind turbines in the manner that you want to get the maximum power. But for this one, we're going to use the Jansen model, as you can see in the screen, whereby we can know that a wind turbine arranged in, in parallel with the wind direction. As you can see, here we have D1 here. This is the first turbine here. And you can see this turbine causes a reduction in the speed of wind to the second turbine, which is here. So if you compare the wind speed here and the wind speed here, we see that the wind speed being experienced in the first turbine is very high because it is the initial speed as compared to the speed experienced in the second turbine, which is given here as ux, which we are going to find out to know the changes. So just be ready, have your materials ready, because I want us to explain this phenomenon and then to use another. We have two examples I'll be explaining, and then I'll give you one question to practice with so that you can be familiar with the model. So once again, this is the energy studies, and it is a course called the wind power and small hydros. It is offered in my university at master's level. So we can just start with the model, and we can see that we have the formula which is used when determining the wind speed in the downstream turbine of the second turbine, which is affected by the wave caused by the first turbine. So using the formula, we can see that it's very simple. We have the speed in the downside turbine, which is ux, and is equals to, then you have uo. As you can see in this diagram, uo is speed experienced by the upstream turbine. And then we have these other parameters. We have CT. CT is the thrust coefficient, as you can see down here. And another parameter that we have is K, which is the wake decay constant. And then you notice that all these parameters make the calculations easier because we have X here, and X is given in diameters, which I get to that. So if you're given X in diameters, which is the distance between the two turbines, so you can have for example, if you have the distance between the two turbines being 5 diameters, we shall just write here 5D. Let me alternate this one. So it will just be 5FD, and then you're dividing by D. So that means the D and D cancel. So for that part, we shall have 5. But then I want us to get to the real equation, to the real example, so that you can understand how easy this is. So we can start with this one. This is an exercise 1. So just go through the question. Maybe 1 minute is enough. And then we shall do it together. I think that's enough. So first of all, we can get the parameters that we were given from the equation, from the question. And I have done this in a separate part. Let me just open it. So here it is. This is the first question. And according to the question, you can see right here, we have two identical turbines, which are 12 rotor diameters apart. Remember I said about the distance being given in diameters. So we have our x being equals to 12d, 12 diameters. As you can see here, this is 12 rotor diameters. And then we are given that we have our K, which is 0.1, and the thrust coefficient, is CT, is equal to 0.7. And then we are going to use the Jansen wave model to determine the speed of wind approaching each of the turbines. Now you'll notice that these two turbines are, are parallel to the direction of the wind. So that means that the wind speed experienced in the first turbine is different from the one experienced by the second turbine, because the turbines are arranged in such a way that, considering the direction of the wind, the turbines are behind each other. So we have one in front and the other one behind the first one. And so going to the equation that we had before, so we can have that. Where is that equation? The equation, we have this equation. So first of all, you should notice that UO, this is the speed experienced by the first turbine. So there's no calculation concerning the first wind turbine because there's no wake. So we are just dealing with the initial wind speed. The wind speed, we shall just leave it at UO. But then when we go to the second turbine, that is when we get the difference in the wind speed due to the wake caused by the first turbine. So just going to the calculation. So we have the speed in the second turbine being given by UO as in the formula. And then 1 minus, and then here in the, let me show you. So this 0.7, this is our K. No, this is our CT. And we have our K here. This is 0.1. And then now notice the diameters I said. We just have the X, which is 12D, but then we just divide by D. So we have D and D cancelling. And then, so we are just left with normal numbers. So we only have two unknowns. We have UX and UO. But when determining the speed in this scenario, we leave the speed UX as a function of UO. Okay. So we can just go to the final calculation for that one. So you can see that UX, if you calculate, you get 0.9609 of what is in the brackets here. So all this. will give you that value, and then we have multiplied by UO. So it's that simple using the equation. But now there was a second question. The second question was to estimate the loss. Now we need to understand we are not dealing with the loss in production. Let me alternate this one. So you can see this one. Get rid of these ones. So you're given that the two turbines have the same rated power, the P rated. And if you are experiencing wind speed at the first turbine being UO, that means it will give you the rated power. So in terms of power, we also don't have to calculate anything in the first turbine, the upstream turbine. But now when it comes to the downstream turbine, we are given the formula being the power is equals to P rated, and then we are multiplying by the speed of wind in the downstream turbine over the speed of wind experienced in the upstream turbine, and then we cube it. So going to my solution, you can see it here. As I said, the power in turbine 1 is just P rated because there are no interferences. And now in the downstream turbine, we had the speed being 0.9609 UO. But now here we want UX over UO. So it's simple. We just divide it here by, let me see. We just divide here by UO. My pen is not that accurate. So we divide UO in both sides. So that you get this one here. The UX over UO being 0.9609. And so the power in the downstream turbine now becomes this value here, then cubed, then we multiply by P rated. So in the final, we have 0.8872 P rated. So in this scenario, we are still going to leave the answer in terms of P rated because we don't know the value of P rated. And now we can determine the total power provided by the two turbines. So we have the first one being 1 power rated and the second one being 0.8872 P rated. And then the total becomes 1.8872 P rated. But now we had two turbines and they're similar in rating and in everything. So that means if they were working at 100% efficiency without the wake, that means they should have been P rated and another P rated. So that means the two should have given us 2 P rated. But now in our scenario, we have 1.8872 P rated. So when we want to calculate the power, the average power of each turbine, we just divide by 2, as you can see here. So dividing by 2 gives you 0.9436 P rated. So this is the average of one turbine. And so if we are going to calculate the loss in percentage, we just need to calculate the the expected, which is P rated, and then we take away what the turbine is producing, 0.9436 P rated, and then we divide by the expected, which is 5.64, and then we multiply by 100 to get it in percentage, and you have 5.64%. And alternatively, you can decide to, okay, starting from what? Instead of getting the average from here, you can decide to work them. We said we are expecting 2P rated, we use PR. So you just take away 1.8872, which is also in P rated. And then all this we divide by P rated, 2P rated, because it is the expected. And then now we multiply by 100. So this will also give you the same answer, 5.64%. So you can have the options. So you can just decide which one to use. Now, that is a case where we have only two turbines. And these two turbines are situated, are arranged in such a way that they are parallel to the direction of the wind. Because if for example, the two turbines were to be perpendicular to the wind travel, so that means they will be side by side facing the wind. So there will be no wave, there will be no reduction in velocity of the wind, there will be no reduction in the power. So that means the two will be operating at 100% efficiency because there's no wave. And now, still on that, there's a question here. Maybe we should do it. Okay, this is just for you to go through. It is in a past paper. And for this one, you can see that there are two identical turbines with each having the power of P rated. And now they are lined up in a row, 8 rotor diameters apart. So that means we have our X being 8D as such. And now they are experiencing wind parallel to the row. So that means if they are parallel, then one turbine is behind the other. And then you're just told to use the wake model to determine the speed of the wind. So this is not different with what we have done, but the difference will just come in here in Roman 2, whereby you are told to estimate the wind farm efficiency. So you shall notice that in the first one, we calculated the loss in power due to the wake. But now in this one, we are calculating the efficiency. So we shall get to that in our next example. And lastly, we have P rated being given. So you can determine the average, the annual energy production from the wind farm, because now you have the value of P rated. So you can go through this question and you notice how easier it is to use the Jansen's model. Now we can go to the second example. Now, this is somehow complicated because instead of having two turbines, now we have four. And these four turbines are arranged in such a way that we have the X being 10 rotor diameters apart. So we already have our X, you can see it there. So now in the case of four wind turbines, we know that the first wind turbine is not affected by any wake. So we shall just use UO. But the first turbine causes a wake which reduces the velocity going to the second turbine. And now the wind experienced in the second turbine is also reduced before it reaches the third turbine, and so on and so forth. So the wind speed keeps on reducing in each and every turbine. And if the wind speed keeps reducing, we expect that the power being or that means the energy being generated, it keeps on reducing. So we shall just get to this one. I had done it also. So let's go to the solution. So we have question 2 here. We have the parameters given. So we know the turbines are 4 and they are identical. And then the power in each is P rated. And then we have our X being 10D, which is 10 diameters apart. And then our K is given as 0.1 and the thrust coefficient is given as 0.75. So let's start determining the wind speed at each turbine. So as I said, the first wind turbine gets UO. So there's no calculation there. But when we go to the second turbine, so U2 becomes, so now we are using the the Jansen's model. So we have U2 being is equals to UO, which is the one before. And then we have the normal equation. We have the thrust coefficient here is 0.75. So this is just similar to the one we did. So you just get U2, which is the spin in the second turbine, being 0.9444. But now in terms of UO. And now I want you to think about what will happen to the third turbine. So if we have the second turbine getting 0.9444 UO, so you should know that the third turbine is expected to get less wind speed than the second turbine. So that means when you go to the third turbine, we have U3 is equals to, now we have U2 here. Yeah, we have U3 is equals to U2. Now instead of UO, which is the speed for the first turbine, now we are focusing on the second turbine because the second turbine is the one causing the wave to the third turbine. So that means that we shall just take U2, but now we have U2 being a function of UO here. So that means our 0.3 will be equal to U2, which is 0.944 UO. And then now the normal calculation here. So we shall just notice that we are still using 10D because we are dealing with the distance between U2, which is causing the wake, on U3. So the distance between U2 and U3 is just 10 diameters apart. So we shall just have the calculation. In the bracket, we get 0.9444 still. So when you multiply them, you get U3 being 0.8919 UO. And now, when you go to the fourth turbine, we expect that the speed being experienced by the third turbine, which is 0.8919 UO, we expect it to be less than that due to the wake in the third turbine. So that means that we shall just use the normal formula. So we now have U4 here is equals to, this is the upstream turbine, which is causing the wake. But now we already know U3 being 0.8919 UO. So this is here. And then we have that in the brackets, still the same because we are just dealing with the same, the distance between the third turbine and the fourth turbine being 10D. So we shall still have the same value, 0.9444. And now when you multiply the two, you get 0.8423 UO. So that is a wind speed experienced by all the four turbines. We have calculated all of them. And now we can go to the second question, the second part of the question, which is determine the total power output given that the power of the downstream is given by just the other one, P is equals to P rated into UX over UO. So we have here UX being the speed of the downstream turbine, and UO is the speed of the upstream turbine. So we can just proceed to B. So as we said, if the wind speed is not affected in the first turbine, that means we are just getting the exact power, the P rated. But now when you go to T2, we shall have U2 over UO being 0.944. I'm sure we had seen that. So it's here. So we just need to divide by UO on this side and on this side. So on one side, you will just get U2 over UO being is equals to 0.9444. And now when we come to the power, we just need to cube or raise that to power 3 and multiply by P rated. So that is where we are getting 0.8423 P rated. When we go to the third turbine, it is the same. We shall have U3 over UO being 0.8919. And then when you cube it, get 0.7095 P rated. And the same case to T4, we have 0.5976 P rated. I hope everything is clear. But then they need us to calculate the total power. So the total power, you just add all those. We have the power in T1, power in T2, power in T3, and power in T4, which is the power in turbine 1, and so on. So you shall get the total being 3.1494 P rated. That is the total power. And then we have the third question, the third part of the question. We are supposed to calculate the efficiency of the wind farm. And now we can see this formula that the efficiency is equal to total energy production over annual energy production. We just calculated the energy production, the expected. We just calculated the real due to the weight. So we just get that real, which is 3.1494. That is the total energy being produced, the total power, which will help us determine the total energy. And so if you have the total power, and here we have, this is the denominator is supposed to be the rated power or the expected, the ideal. And we all know that energy is calculated by the power times time. And so when we're calculating the efficiency, we can determine that the energy, the total energy production will be energy. We have the power 3.1494 P rated multiplied by T. We can just leave it at T, or we can just use the value, but there's no need because they will eventually cancel out. So we have over the P rated, which is the power of the ideal turbine, Then we multiply by the number. We know there are 4 turbines. And then we multiply by T. So if you can see that the P rated and the P rated cancel, the T and the T cancel. So we are just left with 3.1494 divided by 4. But then we want the efficiency in percentage. We just multiply by 100. And here we get 78.74%. It's that simple. But we have another alternative for calculating the efficiency of the wind farm. So we can use that the wind farm efficiency is equals to 1, which is the whole, minus P wake over P free. Now, in this case, the P wake is the loss of power due to the wake. And the loss of power, if you can remember calculating in the first example, we calculated the loss. So in this case, we are taking 4 because there are 4 turbines. So we expect them to give us 4 P rated, but they are giving us 3.1494 P rated. So when we subtract them, we get the loss. And now when we come to calculate the efficiency, we shall just take 1, then we take away this loss now over 4. And since we want it as a percentage, we just need to multiply by 100. And there we get the same answer, 78.74%. So you can use either formulas, the area efficiency formula or the wind farm efficiency formula. And we can proceed. We had another question. So we now have the wind efficiency in Roman 2, according to the question. Now we now go to the last part, where it says if P rated, now we are being given P rated, the value in megawatts, 1.5 megawatts. And now we are told to determine the wind farm's annual energy production. So this is very simple because we already have the annual energy production being 3.1494 P rated. And now the only part that remains is just to substitute the values. So the P rated, it's given in megawatts, but I prefer we change it to kilowatts. So just need to multiply it by 1,000. And now we know that energy production or energy is equals to power times time. In this case, I decided to use the power. As you can see here, is the power in kilowatts and time. But now time, we want it in hours. And since they're saying annual, so we need to determine the number of hours in a year. So we know that we have 365 days in a year, and each day has 24 hours. So we just need to multiply by 24 hours. So that will give us, let me do this. So we shall have 3.1494. This is the value. Just a minute. So we had the 3.1494 from here, and then P rated. So we are just needing to multiply this value by 1500 watts, 1500 kilowatts, which is here, and then we multiply by the time. So our energy becomes 41,383,116 now in kilowatt hour. So this is just like the normal unit we use in our daily lives, the electric unit, kilowatt hour. So that is the end of the quiz. So you can just try and do the question, which was which had two identical wind turbines. So now it is easier because we have done a bigger example. So that is the end of the explanation. You have a good day. Thank you.